Yeah, so hi guys. Yeah, first of all, thank you everyone for coming. And as you guys know, today we'll be covering a workshop 3. So it's an extension of workshop 2, which is on machine learning. Except today we'll be covering regression techniques. Sorry, not regression techniques, classification techniques. But before I start, you guys, if you have any questions later in the presentation, right? Please feel free to address them on this Padlet app, which I think should be on the same set of slides that you guys have. Okay, so just a brief overview of the topics we'll be covering today. So I'll be giving a recap on machine learning, followed by introducing you guys to like what classification is and some of the most common classification algorithms in machine learning. And then we'll go to the collab workbook for some code walkthrough. And then after that, we'll do like a more advanced classification using things like neural networks and deep learning. And then which is followed lastly by the deep learning code walkthrough. Yeah, so just a recap on what machine learning is. So machine learning is so there are a few definitions of machine learning. So this Arthur Samuel says it's the field of study that gives the computer the ability to learn without explicitly programmed. And another guy who has this more complex definition, he says that it's a computer program that is said to learn from experience E with respect to some class of tasks and performance measure if its performance gradually improves with more and more experience, which in terms of the computer programs is more and more trials on your particular data set. But my definition is slightly simpler. It's basically teaching your computer how to make accurate predictions when fed unseen data. So that really is that's all for machine learning. There's really mainly just one purpose, which is to predict something from unseen data. So moving on to the different types of machine learning, there are 3 kinds of machine learning. The first and probably the most common is supervised learning. So in supervised learning, you have labeled data and you're trying to predict the outcome. For unsupervised learning, you have no labels to your data and you have sort of no direct feedback. And the objective here is really to find some kind of hidden pattern or structure. And then lastly, you have reinforcement learning, which is the least machine learning out of the 3, but it's still classified under machine learning. So it's a sort of a decision process where you have a reward system, and then after multiple trials, the computer learns like which decision is good, which decision is bad, and it's basically an action-based kind of learning. So more on these 3 types. Just to give you guys a brief intuition behind AI and machine learning and how that has developed like over the past many years, right? It's been deep learning actually is pretty recent. The first deep learning algorithms started exploding around 2013. And basically the whole idea behind AI and all these buzzwords like machine learning is to mimic how humans learn. So for supervised learning, which is the most common, we want to mimic how you can think of it like learning as a child when, for example, you don't know how to do like some math problems or you're trying to learn English. You need some supervision to help you get started, right? So that's why we are supervised learning. We feed them particular data and then we tag labels to these data sets, and then we run multiple trials on the computer on the algorithm, so that in hopes that when they see something similar next time in the future, they're able to get a good answer to the problem. So that's what supervised learning is. And unsupervised learning is like when you're a child, maybe you're trying to walk or you're trying to run, then you learn it by exploring the world yourself, finding like, hey, this is what works, this is what doesn't. But there's no direct feedback mechanism that allows you to directly learn from it. So that's unsupervised learning. It's mainly finding patterns. And then lastly is reinforcement learning. So a bit more on these three broad classes of machine learning. So supervised learning is basically, as mentioned earlier, the defining difference is you always have labels to the data you are training your algorithms on. So essentially, at a very broad level, at a very high level, what supervised learning is that you're just telling a function to map an input to an output based on many example input and output pairs. And then your input is basically just x in this function, and then you pass it through your ML or deep learning algorithm, which is usually a pipeline, and then you want it to return y. So x can be really anything, and as we'll see later, it can be really anything. X can be English and y can be French. So for example, like Google Translate is an example of supervised learning. So unsupervised learning is basically you're trying to find patterns. So a good analogy would be, imagine you're in a foreign country and you can't speak or understand the language. However, you see people saying a specific word like gaya or this antiosas when parting from each other, and then and the first few times you see it, you don't really get what it means, and you've never heard it before. But over time, after 2 weeks, you keep seeing people saying that when they meet each other and parting from each other, and eventually you'll come to a smart conclusion that maybe it stands for goodbye, and antiosas stands for gaya stands for hello, and antiosas stands for goodbye. So that's essentially what unsupervised learning is. You don't directly tell the computer what it is or what labels it is categorized under, because in these data sets normally it's very big. There's no exact. You don't normally know like the different categories that the different classes are placed into, and then you want the computer to come up with to learn from the patterns and associations with one another. And the last one is reinforcement learning. So so basically reinforcement learning is basically you basically expect the computer to learn from a series of actions. So that it's very good for problems that have binary decisions to be made at multiple steps. So for example, like so games would be a very good one, like Sudoku, chess, or something, or things like that. So there's really there are only two kinds of reinforcement. One is positive reinforcement. So when an event occurs due to a particular behavior, you increase the strength and frequency of that behavior. So you tell the computer that, hey, that's a good thing, and whenever this happens, I want you to make that happen more and more. So negative reinforcement is the opposite of that, and it's basically the strengthening of a behavior because a negative condition is stopped or avoided. So they're basically just opposites from one another. So the best, like as mentioned earlier, the best kind of problems to use reinforcement learning on would be rule-based systems. So, and in particular, rule-based systems which are like binary. So if you do this, if you take an action, this particular outcome will occur, and if you don't, if you take another action, this will occur. So one of the most common, one of the most famous examples of reinforcement learning is you guys will probably have heard of it before, is AlphaGo. It's an AI that beat the top AlphaGo player from Korea. So this this AI algorithm use reinforcement learning. Yeah. So and with that, I'll move on to some of the common classification algorithms. There are quite a few. I think at least 6. So here so today I'm only covering 3 because these 3 are the most common, and they usually for most problems for most competitions like Kaggle data sets or like even schoolwork, usually these three will deliver the highest accuracy. So there's actually really very little point looking at the bottom three lah. So basically, what are decision trees? So basically, decision trees is actually very simple. It comprises of nodes and leaf. So nodes are your decision nodes, and a leaf, which is the bottom of the decision tree, are your outcomes, which are assigned specific probabilities, which is what the model is trying to come up with. So this is an example of a decision tree. So this one, you're trying to get the computer to sort of come up with a decision as to which animal this is. So you feed in. So this is so has feathers, can fly, and has fins. The inputs. So they are binary inputs. So so usually you assign true to number 1 and false to 0. And then so for example, you feed in these 3 zeros, right? And then you feed in let's say it has feathers and it can fly. So it'll give you hawk with a very high probability. But this is just a very simplistic tree. Usually most decision trees have many more variables. And basically that's the whole premise behind it, is that it really just is comprised of many if else decisions. So if it has a particular something, or if something is present, then you move on to that node. Otherwise, you move on to the other node. So an extension of decision tree is a random forest, which aggregates the output of multiple decision trees to make the final predictions. So as you can see in the picture below, right? A normal decision tree is just one decision tree, like extracted from the input that you provide once to your data set. But for a random forest classifier, there will be multiple decision trees created, and each will be randomized, and it will with the same input, but you'll come out with their own predictions from each of the decision trees, and then the majority vote will be taken, which results in a final prediction. So this will increase the probability of making a correct prediction. So usually when you want to use decision trees for a problem set, it will normally always be better to use a random forest. So next will be support vector machine. This one is is also one of the most common classification algorithms. So the objective in SVM is to find a hyperplane in an n-dimensional space where n is a number of different features that classifies the different data points. So if you want to go into the math of it, it's actually quite chim. So I won't be delving into that. But hyperplanes are basically decision boundaries that help classify the data points. And basically data points falling on either side of the hyperplanes can be attributed to different classes. So as seen in a picture below, the objective for most SVM algorithms is to maximize the margin between the support vectors. So support vectors are this one, the ones at the edge of the hyperplane. So we want to minimize the distance, the margin between support vectors, so that you can maximize the sort of the categorization between different classes. So that let's say you have an animal data set, you have like birds, dogs, cats, right? You want to ensure that between all these different data sets, right, you have the maximum margin, so that you have the best chances of differentiating these different classes. So that's the main objective. So when you feed in new data sets, they will check, and then they will assign it a particular space in this n-dimensional space. So in this case, it's a 2-dimensional one. But as you guys know, if it's 10 dimension or maybe even 100 dimension, 100 classes, which is entirely possible, it's basically a 100-dimensional space, which is very hard to visualize. But basically, it will assign it a point in that space, and then based on where it was classified, it will just return the highest probability of which class it belongs to. So the last one I'll be going through today is logistics regression. So I'm sure you guys are familiar with linear regression. So logistics regression is very similar to linear regression, except you you use a logistic function to squash the output between 0 and 1. So this is usually very good for binary predictions. So it's like whether you want to predict whether it's going to rain or not, or whether this particular image of this particular image is a dog or not, or whether someone has a disease or not. So the logistic function is actually the sigmoid function, which is this particular function. So basically, that's about it now. And lastly, is analyzing the data. So whenever you perform your classification, use the classification algorithms on the different data sets, you want a good way to compare it across the different classification algorithms. So the industry standard is really just the confusion matrix, which basically shows the way in which your classification model is confused when it makes predictions. That's why it's called the confusion model matrix. So I'm sure if you guys have taken like statistics mod or any kind of like basically statistics mod, you probably have seen it. You probably have seen it in your math textbook as well. But essentially, it's basically these four true positive, false positive, and true negative values. And then there are the associated formulas with it. And the classification report is just an extension of the values from the confusion matrix. So the recall or the sensitivity it basically refers to how many of this class we'll find over the whole number of elements of this class. And the precision is how many will be correctly classified among that class. And then the F1 score is the harmonic mean between precision and recall. To be honest, it's not really used. The F1 score is not really used that much. It's mostly the sensitivity and precision. And then lastly is the support, which is the number of occurrence of the given class in your data set. So in this case, you have 37.5K of class 0 and 37.5K of class 1, which is a very well balanced data set. But most of the times it's not that well balanced. And then the accuracy is just basically this one. It's basically what you use to the number you use to compare between different classification algorithms. Yeah, so with that, I'll move on to the ML, the code walkthrough. Yeah, so if you guys have any problems opening the Colab workbook, just feel free to ask any of our members for help. So the first thing to do will be to integrate with the required libraries. Jimmy. Yeah, so and after importing the required libraries, we will get the data set from this link. It's actually just my GitHub. So it's the raw GitHub thing where I upload that to my own repo. And once you do that, you just use pandas and basically this is a diabetes data set. And what we want to predict is the outcome, which is 1 or 0. And 1 is basically whether you have diabetes or not. 0 is no diabetes. So this pregnancies, glucose, blood pressure, skin thickness, insulin, like all these variables are what we'll be using to predict this outcome. Wait, give me a minute. Sorry about that. Yeah, so now we'll check out a simple pair plot, which gives us an illustration of the correlation between different variables for this small data set. So this one, so we just run it. I'm using the Seaborn library. So yeah, so this one basically is it's just the Pearson's correlation for all the different attributes. So we want to find out the one that has sort of the highest correlation with the outcome, so that we know what to look for later. So in this case, it will be glucose and BMI, as well as age, which have the highest correlation with the diabetes, which makes a lot of sense. And then now we'll use a sklearn string test split. So if you guys are unfamiliar with this, you can just go over to the sklearn. So you can just go over the sklearn documentation. There's basically all the documentation here. And you don't even have to build your own, if you're just doing ML, you do not have to build your own machine learning algorithm. Just basically use their decision tree or whatever classifiers they have, which they have in their library. You just go and search. And of course, you always want to use their train test split. So firstly, we drop the outcome column, which is a column we are trying to predict. So we drop it and we specify x is equals to 1, which is basically you drop the column instead of the rows. And then we create a y variable, which is as just now you guys saw, right? The supervised learning, right? So our input is all the different x variables like glucose, diabetes, and like whether this person is pregnant or not. But the output is really just the y, which is the 0 or 1, whether or not this particular person has diabetes. So that's what we are trying to predict in this supervised learning model. So we store in y, the outcome column, and we just run it. Okay, and then we use sklearn string test split, and we split it with a test size of 0.20. And basically, test size of 0.20 means that 20% will go to the testing sets, and 80% will be used to train. So yeah. So in this case, so in this case, there are 7, 6, 8 sort of rows in this data set. So which means 20% times 7, 6, 8 will be used for testing, and then the rest will be used for training. So that's a decent amount to be used. Usually you want more than 500. Yeah. So so we'll start with the decision tree model. So we just have to, from sklearn.tree, import the decision tree classifier. And then we fit it to the training data set, which is basically just fitting it to because these models in sklearn, they're already pre-trained, so you don't have to spend time training. Yeah, so the first variable will be the x train data, and the second variable will be the y train, which is what you're trying to predict. So the y train is your labels now, basically, to your primary data set. So you run it, and that's it. And then you just have to run a .predict function, and then you print your classification report, and then you'll get your accuracy, which is 74, and then you print your confusion matrix, which is 80, 22, 16, and 36. So this confusion matrix it's important to put it on the y test, because obviously there's no point putting it on the x test. You'll get 100%. This is what you train your data on. So you put it on a y test, and then you run your prediction, and then you put your second variables to your predictions. and I get a confusion matrix. So for this data set, decision trees has an accuracy of 74%. And now we can look at the, okay, so this one is just is how the, this is just a brief snapshot of how the computer, the algorithm is actually analyzing our data through like the actual decision trees that actually created. Just give it a while for it to run. Yeah, so if you guys are seeing it, so basically, yeah, so this is like the, it's not as simple as the animals one just now. In fact, this is actually a very simple data set already. As you can see, it's actually quite a massive decision tree already. So basically, that's it. I mean, it starts from like it starts from all this, starts from the root node, which is this one, and then you feed in basically all these attributes, less outcome, and then you'll just go accordingly. You'll just branch out the different nodes, and then eventually you'll come to here, which is where you'll predict whether it's a value of 0 or 1, which is whether it has diabetes or not. And then it'll just give you your predictions stored in a NumPy array. So next we'll see how the random forest classifier performs on this. Can it actually do better than the decision trees, which it is expected to. So we'll do the exact same thing. And we'll predict it. And yeah, and it does perform better. You get an accuracy of 77%, which is slightly better than a decision tree. So next is the logistics regression. So in this case, in most cases, random forests and decision trees would perform better than logistics regression. But we'll see how logistic regression actually performs on this, because as mentioned earlier, logistic regression is very good for binary outputs, which for this diabetes data set is a binary output. So there's a high chance for logistic regression to actually do as well. So we can predict it, we print it, and then we print the classification report. So we actually get a 76%, which is actually better than the first decision tree, and actually comparable to the random forest. And then lastly is support vector machines. Basically do the exact same thing, box VC, and we print the confusion matrix and the classification report. And we get an accuracy of 71%, which isn't the best for this data set. Usually support vector machines and random forests deliver the best results. But for support vector machines will usually tend to work better if you have multiple classes. Like let's say it's not a binary output and you have like multiple different classes of animals to categorize in, for example. So next is a different data set. This time is for you guys to try it yourself. But I'll just walk you guys through the first part of it. The first part. So this is a slightly bigger data set, and it's just a lone data set. So you can play around with the data set. So there are, sorry. So this data set is pretty big. There are 9578 rows and 14 columns. And basically what we are trying to predict is basically the last column, not fully paid. So basically you're trying to predict the the probability of a customer paying off his loans. And 0 is obviously he doesn't pay it off, and 1 is he pays it off. 1 is he does not pay it off, and 0 is he fully pays it off. Yeah, so basically this one is just visualize this code is just to visualize the data. Same thing, I'm using Seaborn. And then, why this data set is, this data set is actually more representative of what you actually see out there. Because this diabetes data set is all numbers, so it's very nice. But actually, you'll find that most data sets out there actually have what you would call categorical variables, which are things like purpose, so like debt consolidation, credit card, or other. Computer can't exactly read that because it doesn't know what's the difference between this and it's like debt consolidation and credit card, or credit card and all other. So what we want to be doing is we want to be converting these categorical columns into numerical variables that we can feed into the algorithm, which has to be NumPy arrays, and NumPy arrays you can't really put strings in them, so they're matrices. So we have to convert these columns, purpose, into sort of a categorical sort of numerical variables. So that consolidation will probably stand for 0, and credit card is 1, then all other will be 2, and home improvement will be 3. So that's how you compare between the different purposes. So fortunately for sklearn, there's a very fast way of dealing with these columns. You don't have to create your own functions to convert it into categorical features. So basically, you just use the df.dummy function, and pd pandas.getDummies to create the encoded columns on the purpose column, and then you concatenate this to the original data frame, and then of course you drop the original purpose column, which have strings that cannot be fed into the model. So you extract the purpose column, and you find the number of unique categories is 7, and then you just run the get dummies thing. Drop first is basically just dropping this purpose. So basically you run axis equals to 1 to concat along columns instead of rows, and defaults to 0. So this one is basically just doing what I just described now. So in place attribute basically is so that I don't have to assign it. Like if I don't use the in place true, I'll have to do like something like this. But now I don't have to. It has it in place now. And then after that, over here I actually drop the not fully paid column, which is what we're trying to predict. And then I assign y to it, which is so this will be the column we're trying to predict, and then all the other variables are what we are feeding into the model. So how does the new data set look like? In a minute. So I'll run this first. df3, so df3. So this is the new data set. And if you scroll to the right, you'll see that there are these columns, which are your dummy columns to differentiate between the different purposes. So if there's a 1 here, means this person is a credit card. His purpose is credit card. So if there's a 1 here, is debt consolidation. So on and so forth for the rest. It's quite simple to understand. So, and next is the heat map. Basically the correlation between all the different variables. Same thing, you can take your time to analyze it later. And then now is a time to basically just use sklearn and whatever classifier of your choice to fit the data and make the predictions. Yeah, so I'll give you guys some time to work it out yourself. At the same time, we'll be stopping for a 20 minutes break. I'll be coming back at 8:05. Okay, hi guys. Yeah, so now I'll be resuming on from where we left off just now. So basically for this data set, I used I just I equated y to the column we're trying to predict, which is a not fully paid column, and then I create x, which is the list of variables that we're trying to feed into the model, to x, and then we fit in the train test split and the test size of 0.20. And then I decided to use a support vector machine simply because it usually delivers the highest accuracy amongst like different models. And with that, we get an accuracy of about 85%, which is not too bad. Yeah, so if you guys have managed to come up with a higher accuracy, you can feel free to let me know like which model you use and how you clean the data sets or if you did. Yeah, with that, I'll move on to the second part of my presentation, which is deep learning. Yeah, so deep learning is I'm sure you guys will have heard of it before. But it's a subset of machine learning, and it's not anything more special than machine learning. It really just is the same thing. You're trying to predict something from unseen data, and and basically it's deep because of the many hidden layers in the network, as you can see represented by the yellow circles. So it's a form of predictive learning as well. So basically why it's called so deep learning comprises mainly of neural networks. So why it's called neural networks is because it mirrors the way because the researchers or all these like deep learning experts, right? They like to call it all these layers as neurons. So you have the input layer which passes information to this sort of hidden layer which passes it to this, and in the hidden layers there'll be like math functions that will be applied at every stage of the hidden layer all the way to the output, which I won't be covering because I'm also not too sure about the exact math behind it because it really is quite complicated. Yeah. So basically, the rationale behind deep learning is to improve accuracy over your traditional machine learning algorithms. And basically, deep learning unlocks more possibilities rather than just traditional like data sets like what you have seen in a code walkthrough just now. So when you want to predict images or you want to perform more complex tasks like sentence translation, then deep learning would be more appropriate. Which is why when deep learning exploded in 2013, we like in a span of a few years, right, we had a lot of sort of new things coming out into the industry. So things like Google Translate, with like your Amazon like self-driving cars and all that, right? So basically, for deep learning, there are mainly two kinds of classification: images or text. And the same thing is a form of supervised, usually supervised, and we have to create labels to tag these data sets. And then our output is a set of fed labels that we use to tag these data sets. So if you're feeding in a group of images and your labels are cat, dogs, and elephants, your output layer will always be within the set of cat, dogs, and elephants. You will never be able to predict something else. So that's just a limitation of just like most machine learning algorithms in general, that you can't expect the computer to predict something that you have never let it see before. So moving on, continuing the example that I just shared with you guys. So this is just an example of a input tagged to its particular label, which in this case, the image of a cat is tagged to the string cat, and then a dog, the image of a dog is tagged to the string dog. So how deep learning works is really by sheer iteration itself. So if we feed a computer one image of a dog, we tell it's a dog, and we feed it and then we feed in a random image of a dog, it probably won't be able to predict. But after feeding it many times, like maybe 1,000 times or maybe even 10,000 times, different images of dogs, and then labeling it as dog, you would expect that when you feed it an unseen image it's never seen before, it's not in this set of images that you use to train your model on, that it will be able to predict with a very high accuracy that's a dog. And that's just a brief example of how deep learning works. Another common example is self-driving cars. So this is actually the main technology fueling self-driving cars, like self-driving technology in like cars like Tesla or the NVIDIA technologies. So yeah, so that would be more convolutional neural networks, which are used for images. Another form of neural network is recurrent neural network, which is mainly used for text. And what we're telling the computer to do is to process information based on previous information. So there's a lot of math involved. This is usually master level PhD stuff. I mean, if you are taking like a specialization in AI, then you probably learn all this as well. Basically, this is just an architecture of a recurrent neural network, and I'm not going to go into like the math of it, just because it's very boring. Basically, you have an activation function at each of these blue color nodes, and then it's mapped to like usually a binary output, which will allow previous outputs to be used as inputs for the next hidden layer, and then a similar or different function will be used to repeat the same process, and then you'll go on for as many layers as you have built in your model, all the way to the final output. So CNN is usually used for images, as mentioned earlier, and convolutional neural networks are specific neural networks that basically allows you to process images, because images have what you would call RGB channels. So you guys can go and read more about it. But basically compared to CNN provides a way to sort of flatten and pull these image data sets into matrices, and then feed it into the deep neural network, so that we can compare like across different images, and then we can see like some kind of similarity between these images. So that's what the neural network helps you achieve. So some of the common uses of neural networks or deep learning is speech recognition. So in this case, your input is audio and your output is text, as seen commonly by Google Assistant, Cortana, and Apple Siri. And another one is machine translation, which is like Google Translate. So your input might be English, your output is maybe Bahasa Indonesia. Another one is image captioning. So your input is image, and you want it to predict some form of text, like maybe a dog, or maybe a boy running in a playground, or something like that. Another one is sentiment analysis. So your input is text, and the output is rating. So for example, you can analyze Twitter tweets, and then you can rate it a score of 0, whether it's more negative or is it more positive. Another one is music generation, where your input can be music notes and your output can be music. Yeah, so with that, I'll be walking you guys through the two examples I have. These are image data sets. I'll just be going through the image data sets today. And if you guys are interested in like text, you can go and include a link also if you guys are interested. But the main API we'll be using is TensorFlow and the Keras API. So this is an industry standard, along with PyTorch that are used for deep learning. And unfortunately, if the Keras wrapper provides a more easier to read API for the TensorFlow library, but it's still quite, I'll say it's still quite complicated. So yeah, I mean, you need some experience if you're like a beginner to this lah. But fortunately, the Keras offers like a pre-built data sets, which I'll be using one of them later. And they also offer pre-built convolutional neural network models that have been trained on like massive data sets on like ImageNet, Kaggle, and like and whatnot. Anyways, we'll see later. Yeah, so so firstly we'll mount the collab thing. So we mount G drive. So this is I mount it so that I can load in like my images later for the model testing part. So as usual, I'll import the necessary libraries. And then what I've done here is I built a custom class to read in your class data sets and then process everything. So basically, this is a simple deep learning model from scratch. So it includes all the methods you can go and play around with it and modify it if you have the time. So basically, just has all the necessary methods to load the data, process the data, and then pre-process the data, visualize the data, and then to initialize and execute the model and generate the predictions. So yeah, with that, I'll just run it. So I'm using the fashion MNIST data set. Give me a minute. Yeah, so this fashion MNIST data set, right, is yeah, so as you can see, basically just now what you use is basically this one, fashion MNIST data set, which is an alternative to MNIST. Yeah, so once I've done and I visualize the data, you see that there are actually just 9 outputs you want to predict from the images that you feed in. So one is the ankle boot, t-shirt, dress, pullover, and like sneaker and whatnot. And after that, we process the data. So I'll just briefly go through my code. So basically, in the initialization method, I basically create all these attributes, which is exactly the same as what I did as the ML thing. Basically, you have train X, train Y, test X, test Y, which you will split later. Which and fortunately, I think if you're loading it from Keras data sets, they already have this load data function which splits it for you. And then this dimension is just the images. It's just the dimension of the images, and then we just want to store the dimension which we have to feed into the Keras model over here, so that the convolutional neural network knows what to recognize. So yeah, so this part is just basically just some pre-processing. So for the label names and whatnot. Yeah, so and then this part is just visualizing the data set is what it's just this part here. And then for the process data, I basically just reshape the data into just one very neat NumPy frame, and then I divide it by 255, which is the maximum number of colors in a 8-bit color scheme. To the power. This is to make it faster for the computer to process. Basically, RGB channels is from 0 minus 2, all the way to 255. So if you over 255, the numbers in your NumPy matrix will be kept between 0 to 1. Yeah, so this part is, and the next part is we initialize the model, and we feed in the dimension of the images, and then the name doesn't really matter. And then these are your quote unquote deep layers. And the activation, normally people just use redo, which is your activation function. And then you just feed in, as mentioned earlier, the inputs goes into the next layer. So the output of this, which is X, goes into the next input layer, and then so on and so forth. Then you just keep feeding feeding until you get the output, which is which you get your softmax function. I mean, which is like your last layer. And normally people just use a softmax activation function. Yeah, so and basically the rest is just following the API lah. Yeah, and then this part is just creating defining the loss function. So in this case, so Keras has a few loss functions. One is there's categorical cross entropy. There's also like binary and sparse and all that. So for this one, because we have 9 categories, so I chose to use sparse categorical cross entropy. And then for the optimizer, I would say there are a few optimizers like RMS, prop, Adam, but usually the industry standard is just to use the most commonly used is Adam. Yeah, so and then execute is basically just running the model, and then the epochs is just the number of sort of iterations that you run it on your training data set, which you'll see later. So over here, I process the data. I process both the train and test data set, and then I execute the model, which is basically training it. So I'll feed it on like 20 epochs. So this is actually a very simple data set. So it takes a very short time. But if you're training it on real life data sets that are that's not so nice like all these, right? Like the ones you see in like Kaggle or like Twitter or like Flickr data set that you should see later. It usually takes about a few days if you have a good GPU, like an NVIDIA Titan or something like that. So that's what the data science teams and like all the like NVIDIA and Amazon they're doing. Yeah, so this is like the accuracy which should be improving as a function of high epochs. And of course, naturally you'll just like plateau at particular accuracy. So we currently have an accuracy of 92%. So this is just two charts of how the accuracy is done as a function of the number of epochs. And the loss, which is also like decreasing as a function of epochs, which makes a lot of sense. And then over here, we generate like our predictions. So prediction, the first one is a pullover, and the corresponding data is this one, which is correct. And then this one's a shirt, which is also correct. This one's a pullover, which is also correct. And dress, this one's also, the fourth one's a dress, which is also correct. And the trousers is the trousers also, and so on and so forth. And this one's a bag. Yeah, so you can see it does pretty well. You can play around with it. So it's not too bad because it's a very clean data set. So and you can probably get about 95% accuracy with this. Yeah, and the next one would be image class prediction using the Flickr 8K dataset, which is where it starts to get really like difficult, which is actually the next learning point for like a lot of the deep learning models. Because right now a big problem is that for like most deep learning models can only give like one word labels very accurately. So if they want to classify like this particular image is a red traffic light or is a green traffic light, that's very easy. They can do it like 100%. Or this particular image is a human. They can do it very easily. But if you want to go into more details, if you provide images that have more noise, like a background and they are not so clean. So like, let's say you have a child, and then beside him there are also other children. Then the current deep learning models have not yet achieved like a very high accuracy with all this, which we'll see later in a Flickr 8K data set. These are real life images. So I'll just import the necessary models. So for this one, I'll be using the exception model. So Keras has many different models. I just chose the first one, to be honest. So if normally the industry, what people normally use is exception, VGG 16, 19, or the ResNet models. Yeah. And then basically these are trained on ImageNet these are trained on ImageNet images. So you can look at it as loads of images they can sort of train your deep learning model on. So yeah, this is like this is what you will be doing if you're planning to go into like machine learning or deep learning in the future, which is pretty hot right now. Even like a normal business companies like Procter and Gamble, or not even tech companies like even like LVMH and all that, right? But your normal companies are also looking for people with like machine learning and deep learning expertise. So same thing, that's why I created like custom functions to like set up the libraries and whatnot. So this part, okay, so I actually just use this function. This one is just creating a list of JPEG absolute paths to the JPEG images for sequential reading into the function later. So I'll show you guys my Google Drive right now. So this is like let's see. Yeah, so this is the Flickr 8K data set. It's in my Google Drive. These are all like the actual images. They're not pre-processed. Okay? Unlike most of these are actual images, which makes it very hard to predict on. But we'll see how the performance of the model is. So I load it in from my G drive because I already mounted a G drive, so I can just load it in. And then I base 098 images. And then you'll see like over here I just picked the first 5, I believe, of the absolute image paths. So basically if you're not running on Colab, it will be like your C drive, like C drive, your name and documents and the particular image, basically your absolute path. And then I load in the model. Yeah, so as you can see, there are many layers in this model. It's actually, I mean, I don't want to go and read now. I mean, but basically, this is an input layer. Then it just convolves many hidden layers until the final layer, which is like the output and your predictions are advanced layer. And then they pool it and whatnot, like max pooling and whatever to optimize it. So, and then this part is basically a helper class that I created to integrate with the Keras model. So I initialize this create predictions class with my JPEG path list. So you guys can play around with it later. But basically this is basically just this whole list of absolute paths. And I just fit it in to my model. And then I select the images. I randomly sample from my image paths. So for the purposes of a presentation, I just seeded it at 7. And then I process the images. In this case, I have to resize the image to 299 by 299. So I use the image to array function. I load the image, the target size of dim and dim, which is basically 299. That one why 299 is because the exception model takes in 299, as it expects 299 as an input, as you can see here. So the input layer for the exception model is 299 by 3. And this 3 is the RGB channels, the red, green, blue channels for the colors. And then this 299 is the dimensions of the image, pixels. So after this part, I process the image, then I concatenate all of them into the format that is required by the Keras model. And I just have to run the decode predictions function, which predicts it which uses the model object, which I'll be feeding in this case, the exception model. And then I predict from the NumPy image array. And then this is just a accessory function to help me display all the images sequentially. And after that, I'll get the top predictions basically I just enumerate through the entire prediction list and then create the prediction label. So wait, okay. So over here I create a new prediction object, and basically it's taking a while because it is running the model, processing the images, is getting the sample, and then it has to run the model also. And then we then generate the predictions by feeding in the exception model into the predict image method. And we get the top predictions and we display the images. Yeah, so these are like the predictions. So unfortunately for this ImageNet data set, they can only predict like one word. So usually if let's say you want to predict like if you want a deep learning model to predict, like, let's say from this image, a man carrying a baby boy with an umbrella, holding an umbrella, that is very, very difficult to do. Like if like you manage to do that, right, you can probably it's like a sort of a revolution in deep learning already. Right now, they're still not able to do it like with a very high accuracy, and it's what they're all like the PhD researchers are trying to do. So from this model, right, actually they managed to get most of the images correct now. So like there is an umbrella, and it's not a snowmobile, it's actually a pair of skis, but I mean, the context is correct. And then this one's a dog, and this one's wrong. It probably has not seen this kind of image before, the model. So it just gives out some random, random name. So basically, like if you notice how I get this probability, right, is that I basically, when I get the top predictions, right, what the model returns is a list of labels tagged to the probability. So what I'm trying to do here is to just extract the top predictions. So my prediction array is sorted. I just get the first and the second, and I just return it with and then I print out the accuracy. And yeah, basically, and then the last two are dogs, which they have also predicted as dogs. Yeah, with that, that's basically it now. Does anyone have any questions? You can post it on post it on a Padlet app, or you can ask me later. If not, you guys can just help me fill up this feedback form. And if there's nothing, I think we'll like really, are we gonna like take photo or something?
Oh no, it's okay.
Yeah. The person who asked, right, basically when you, I don't know whether you fixed it already, but basically when you run this for the first time on like a new runtime, right, you need to leave. But basically, when you run it on a new runtime, you just click on a, I think like I need to reset the runtime. But basically, there'll be a blue link, right? And then you just click on a blue link to mount it. Yeah, okay, so if there's nothing else, right, I think if there's nothing else, I think we'll just end it here for today.